I am Chandler, Klüser, Chantre, and the title of my work is A New Approach for Solving Radiative Heat Transfer in Non-Participating Media. The co-authors are Professor Maurício and Professor Guenther. I am going to follow this outline, which consists in these topics: a brief introduction, the model presentation, results achieved using the model, conclusions, and then the references. The motivation of this work is based on an alternative method to solve radiative heat transfer system with non-participating media. The application of this method can be found in air and space vehicles, like balloons and spaceships, for instance. The objectives of this work are to present a general formulation for radiation problems with multiple surfaces, to introduce in that formulation multimode heat transfer, such as convection and conduction, for example, to find a solution of problems where there are two or more radiative enclosures. As any model, there are some simplifications that we need to assume. They are: all radiant surfaces must have uniform properties along its area. All radiant surfaces must be opaque. All radiant surfaces must be gray or black. There is no participating media between the radiant surfaces. The problem is in steady state. All radiant surfaces must be diffuse, and all radiant surfaces have unique heat transfer parameters to each one of them. Supposing that we want to solve a radiative heat transfer problem with n surfaces, the model proposed will represent its behavior in 3 times n equations, which can be grouped in 3 parts. Our model permits the introduction of other heat transfer modes inside the radiative system, which must be represented particularly for each new problem. For example, the equation below, we can see an equation where there is a modeling of a heat source and also a convection. The 3 groups of n equations, totalizing 3 times n equations, will be placed in a linear system with this appearance. Nonlinear phenomena must be linearized in order to be added to the linear system, like we are going to present in one of the results achieved. The first group of n equations is presented in the first line. It gives how much a radiant surface will contribute to the radiative heat transfer mode to the system depending on its emissivity. The second group of n equations is presented in the second line. It distributes the total radiative heat flux of a radiant surface to other surfaces which is in the same enclosure. The third set of equations is separated in 2 parts that sums n. The first part has n1 equations. The second part has n2 equations. Both of them tell how the radiative system is related to the environment. It is kind of a boundary condition that, in this work, is defined as load. The loads can be represented by prescribed heat fluxes or prescribed temperatures. The N1 equations represent the heat flux loads, and the N2 equations represent the temperature loads. Now that the model was presented, we are going to apply it to two examples and show how the method works in a practical way. The first problem is a long square duct with a convection mode in one of the surfaces of the radiative system. The loads of this problem are: for the surface number 1, a temperature load of 300 kelvins. For the surface number 2, a heat flux convection load, which is nonlinear. The equation for this surface will be linearized later. For the surface number 3, a temperature load of 400 kelvins. And for the surface number 4, a heat flux load of 0 watts, which represents an adiabatic radiant surface. The entire linear system is presented here. The first 4 equations of this system are the first group in the model presented in this work. The second 4 equations, the second group, and so on. To keep in mind, the whole radiative linear system will have 3 times n unknowns. They are the radiant surfaces, radiosities; the radiant surfaces, black bodies, emissive powers; and the radiant surfaces, radiative heat fluxes. Note that the second equation of the third set is referred to the convection load. Once the entire linear system is proportional to the fourth power of the temperatures and the convection is proportional to the first power, the linearization technique will have to be applied. A beta factor was created to linearize the convection load and make it proportional to the fourth power of the temperature of the second radiant surface. This technique will make the system of equations linear again, at the cost of making an initial gas, which is also presented in this slide by the temperature of the surface 2 solution, which is raised to the third power. Making an initial gas of 380 kelvins for the surface 2 and solving the linear system iteratively, we can see that the solution converges. The quantity of iteration steps will depend on the initial gas and the convergence criterion adopted. The linearization technique should be analyzed to check whether the system will converge or not. Now that we presented an example of N1 enclosured problem, this second one will present a 2 enclosured radiative system. To keep the problem simpler, it does not have nonlinear loads, although it could. This problem is a long duct with hot oil inside, which keeps the inner surface at a temperature of 500 kelvins. There is an intermediate surface that separates the oil duct from the neighborhood, and the neighborhood is at a temperature of 300 kelvins. The method proposed gives the following linear system of this slide. Note that the 2 temperature loads were placed in the third group of equations of our method. But there is not a load for the second surface, neither for the third one. It is given that the intermediate duct has a very thin layer of metal, So we can suppose that the temperature of the third surface and the second one are equal. Given that, we can write that their black body's emissive power are equal to, and it is also known that the whole heat flux received by the second surface is given to the third one. Thus, summing the second surface heat flux with the third surface heat flux will have to be 0. Solving the linear system, we can see the results presented in the right side. Note that the surface heat fluxes are all equal with alternating signs, revealing that the all heat received are transmitted to the next surface. We presented an alternative formulation to solve radiative systems. Its advantages over the electrical circuit method are: there is no need to apply electrical circuits formulas to solve the problem, and the method can be applied when there is more than one enclosure in the radiative system. These are the references needed to present this work. We would like to thank the audience for the attention. We are available for doubts and comments. Our contacts are also given below.